Okay, so we've talked about linear combinations, and one of the reasons we like linear combinations is because if you think about what happens when you take a linear combination of vectors, you get another vector in that set, or sorry, in the vector space that's not one of the original vectors that you started with. There is potentially not one of the original vectors that you started with in the linear combination. So taking linear combinations of other vectors gives us a way, or sorry, taking a linear combination of vectors gives us a way to produce other vectors. And so a question that we can ask is, given a vector space, what's like the smallest set of vectors that we need so that by taking linear combinations of those vectors, we can get every other vector in that vector space. And as we will see, that is called a basis. So again, I'm assuming that you know what a basis is already. I'm just refreshing your memory here. So let's build up what the idea of a basis is from the ground up. And then at the end, we're going to see why we really like this idea of orthonormal vectors. Okay, so there's going to be several definitions. So if we've got some vectors, v1 through vm, and for now, I'm just going to imagine that these are in n-dimensional complex space, but all of the definitions I'm making here are going to work for any vector space that you want to think about, but I just want to keep things a little bit concrete psychologically in n-dimensional complex space. So let's say these are vectors in n-dimensional complex space, then their linear span, so this is the term that I'm defining, their linear span is the following set. It's denoted like this. So L, and then we'll put the vectors. So this is like a fancy L. So V1 through Vm. Okay, so this is going to equal to all of the sets of linear combinations. So we're going to look at sums of the form k equals 1 to m, ck, vk, such that the ck's are complex numbers. So again, this literally just means the set of all linear combinations. Another way that we could write this, if we come down here, I'm going to define a matrix whose first column is going to be V1, whose second column is going to be V2, all the way up to Vm. Okay, so this is not, I'm just saying, this equal sign goes with that equal sign. This is like a separate, I'm defining what I'm about to put here. So we could also define this, given what we said in the previous videos, we could also define this as all of the vectors of the form V times C, where C is a vector in Cm, like this. Okay. So again, we take any set of vectors, form the set of all linear combinations. That gives us something called the linear span. Okay. So here's some facts. One, the linear span of a set of vectors is a subspace. Okay, so what is a subspace? This is a non-empty set. Sorry, I'm running out of room. That says non-empty. And if V and W are in the set, then so is any linear combination of them. Okay, so this is clearly going to be a subset of Cn, but it actually has this additional structure of being a subspace. So this means if you take two vectors in this linear span and add them together, it's still going to be in the linear span. And if you multiply any vector in the linear span by a scalar, that's going to stay in the linear span. Okay, and also it's not empty. Notice if we take all of the c's to be 0, or equivalently c equals the 0 vector here, it shows that the 0 vector is in the linear span of these vectors. So that shows that it's not empty. So 1, the linear span is a vector set, is a vector space. 2, the vectors v1 through vm form a spanning set. For that vector space. So what is a spanning set? A spanning set for a vector space is a set of vectors whose linear combination is equal to that vector space. So just sort of by definition, these vectors form a spanning set. Okay. Yeah, so like I said, the linear span is a subset, or sorry, a subspace of Cn. Not just a subset, but it's also a subspace. Okay, but now we can start to ask questions like, well, can we remove any of these vectors and still get the same set? Okay, in other words, if I remove one of these vectors, is it going to be possible for me to remove one of these vectors, but the linear span still be the same? Okay, so that's what I want to talk about now. So it's going to take, I'm going to leave this all here because I want this to sort of guide some of the conversation, and then I'm going to put the new stuff over here. So a set of vectors and maybe I'm going to use W to denote my vectors, so we just keep the V's over here. A set of vectors, W1 through Wm, okay, maybe the m's can be different, are linearly dependent. A set of vectors are linearly dependent if at least one vector is in the linear span of the others. Okay. So a set of vectors, W1 through Wm, we say that set is linearly independent, and actually set here is singular, so we should say a set of vectors is linearly dependent if at least one vector is in the linear span of the others. Okay, so again, let me say that one more time. A set of vectors is linearly dependent if at least one vector is in the linear span of the others. So what this means, so let's say, for example, let's say that W1 is in the linear span of the vectors W2 through Wm. Let's say W1 is in the linear span of the vectors W2 through Wm. In other words, we can write W1 as a linear combination of those vectors. Okay, well, note what this means then is the linear span of all of the vectors, so weird W, W1, W2 through Wm, the linear span of all of these vectors is just equal to the linear span of these vectors W2 through Wm. Because I'm just taking linear combinations of these vectors. And any linear combination that includes W1, well, I can write W1 as a linear combination of these guys, so really any linear combination of the vectors W1 through Wm can be written as a linear combination of the vectors W2 through Wm. So like these two things are equal to each other. So this set right here, there's like there's by adding W1 to this set, by adding W1 to the set W2 to Wm, we're not adding any information. There's no vector that we can get to in this linear span that we cannot already get to in that linear span. So that's why they're called linearly dependent. Okay. Now, if this condition does not hold, if none of the vectors are in the linear span of the other vectors, we say the set is linearly independent. Okay. But let's just talk for a moment about what some of these things might imply if we look over here. Okay, so again, this is the set of vectors and what it means for them to be linearly dependent. So let's see. I think I'm going to have to erase this. Okay, so let's assume. Let me just illustrate something. Assume that V1. So now I'm sort of referring to these vectors over here. Assume that V1 is in the linear span of V2 through Vm. So let's say that V1 is in the linear span of V1 through Vm. Okay, and in particular, let's say that V1 is going to be equal to the sum k equals 2 through m, and I'm going to use the letters bk, vk. Okay, observe what we can do here. So let's say I have a vector v that is in the linear span of v1 through vm. This, in other words, is equal to the sum k equals 1 to m ck vk for some choice of scalars, ck. Now notice what I can do. So I have this right here. This is one way that I can express v as a linear combination of the vectors v1 through vm. But notice what I can do. I can sort of split this apart, and I can look at the v1 sum. So I'm going to have the sum k equals 2 to m c1 times bk vk. Okay, so this, if I take k equals 1, I have c1 times v1, but I can write v1 in this way, and then I'm going to have the rest of them. So I'm going to have the sum k equals 2 to m times ck vk. But notice I can combine this into one sum, and I have the sum k equals 2 to m, and let's see what it's going to be. We're going to have c1 bk plus ck vk, like that. Okay, so note what this tells us. So I'm going to write this just below this. I'm going to write this as the sum, what I had before, k equals 1 to m ck vk. Okay, so now going to erase this. Okay, so this is my vector v, and I'm expressing it as a linear combination in two different ways, this way and this way. So the vector v, little v, is equal to this matrix v times the column vector c1, c2, all the way down to cm, and this is also equal to v, and now I can think about what's going to happen here. If I look at here, this is just a linear combination of the vectors v2 through v3 up to vm, but v1 is not included, so it's going to be 0, and I'm going to have c1 b2 plus c2, and then if there's a third one, c1 b3 plus c3 all the way down to the n cm C1 plus BM plus CM, like this. Now notice what I've done here. I have written V as a linear combination in two different ways. In other words, if I think about the equation V times an unknown vector, big V times an unknown vector is equal to V, I've got two different solutions. Okay, and this is one of the hallmarks of a set of vectors being linearly independent. That when you put them in a matrix like this, then there's going to be either 0 solutions or 2 solutions to an equation like V times this is equal to that. Okay, so keep that in mind. So this is an alternative way. So the vectors V1 through Vm are linearly dependent if and only if the matrix V times C equals 0 has more than one solution. That is just a consequence of what I had on the board before. So convince yourself of this fact. So I'll just maybe show you why this might be true. If I know that V, let's say, times W1 is equal to V times W2. So that would be like what I had before. I had V times the C1 through Cm vector, and then V times the 0, C1, B1 plus C2, that vector. They were equal to each other because they both equal that vector V. If this is true, then I can subtract, and this says V times W1 minus W2 is equal to the 0 vector. Now, if W1 and W2 are not equal to each other, this is not going to be the 0 vector here, and so we have another solution to V times C is equal to 0. So if C is equal to the 0 vector, this is going to be true. So there's always one solution, that is C is equal to the 0 vector to this equation. Okay. So in other words, a set of vectors is linearly dependent if and only if VC equals 0 has more than one solution. Okay. You might remember from your linear algebra class, one way to determine whether or not a set of vectors is linearly dependent is you put them into a matrix and you row reduce, or you compute the determinant. If the determinant is 0, then you know the set of vectors are linearly dependent. But that's sort of equivalent to this fact right here, because when the determinant is 0, it means the matrix is not invertible. Whenever we have more than one vector that satisfies this equation, the matrix can't be invertible. The matrix can't be invertible because there are two vectors that get mapped to 0. So the inverse of 0 is not defined as one vector. It's a set of vectors. And so the matrix is not invertible. And that sort of thing we're going to talk more about. In invertibility of matrices and stuff like that, we're going to talk more about as the semester goes on. Okay. Again, so the vectors V1 through Vm are linearly independent if and only if Vc equals 0 has more than one solution. Okay. So this is sort of, I asked a question before, given a vector set, can we find a smallest set of vectors such that every vector in that vector space is a linear combination of those vectors? The linear dependence and independence addresses the smallest part, okay? So the set of vectors V1 through Vm are linearly dependent if and only if this is true, and we could say the vectors are linearly independent if the opposite happens, if and only if this equation has one solution. Okay. So a set of vectors is either linearly dependent or independent. Okay. So think about that for a second, or keep that in the back of your mind. We're going to move on to another concept. a set of vectors v1 through vm is a spanning set for a vector space, and this is including a subspace, so INCL subspaces. So we could have a spanning set for a subset, or for a subspace. A set of vectors v1 through m is a spanning set for a vector space if the vector space is equal to the linear span of the vectors v1 through vn. Okay, or an equivalent way to say that is if v is in the vector space that we're talking about, then the equation vc equals v has a solution. Okay, so just by definition, a set of vectors is a spanning set for its own linear span. Okay, because what we're saying is spanning set of a vector space, a set of vectors is a spanning set for a vector space if the vector space is equal to the linear span of those vectors. Okay, and so now what we're saying here, okay, is that we're defining the linear span of a set of vectors is a vector space. So by definition, these a set of vectors is a spanning set for its linear span. I mean that seems obvious. But I mean the idea here though is that we have some vector space, and then we want to go into that vector space and pull vectors out of it to be a spanning set. Okay, so it's the order in which you do things, right? So here we have a set of vectors, and then we can just form its spanning set. That's a vector space, and these vectors are a spanning set for its linear span. But typically what happens is we have a vector space, and we want to go in and find vectors that form a spanning set. Okay, so we have these two ideas, linearly independence or dependence, sort of different sides of the same coin, and spanning sets. So the way that we can kind of write this in terms of matrix vector multiplication and systems of equations, so VC equals 0 has exactly one solution. It means the set of vectors v1 through vn are linearly independent. And I'm just going to write that as linearly ID because I'm running out of room to write independent. Okay, and VC equals V has at least one solution, and this is going to be for all v in the vectors, all little v in the vector space that we're thinking about. Then the vectors form a spanning set. Okay. A linearly independent spanning set is a basis. Okay, now I'm missing a word here. So a linearly independent spanning set is a basis, but typically, whereas for a linearly independent set of vectors and a set of vectors that is a spanning set, we don't care about an order. For a basis, we do care about an order. So it should say an ordered linearly independent set. Okay, And for that reason, instead of using curly brackets for a basis, a lot of times we'll write it like this. V1 through Vm with brackets, with these square brackets. Okay, and so it is strictly, in a strict sense, it is not equal to if we do like V2, V1 up to Vm. Okay, now in terms of sets, these are equal to each other, but the order of the bases is important for something that we'll talk about in just a moment here. Okay, so even though these sets, in terms of sets, they're equal and they span the same space, we do not say they are the same basis because they are in a different order. And the order for a basis matters mostly for bookkeeping reasons that we're just about to talk about. Now I need to decide what I want to erase. Okay, I think I'm going to give an example because things are a little abstract right now. And I have prepared an example that I know I'm going to use for the Graham-Schmidt process. And so I'm also going to use it for this to explain this as well. Okay, so I just need to flip to my page in the notes that has the vectors here. Okay, so we're going to look at three vectors. Let me just pick this up for a minute so I can look at them. So let's say V1 is equal to 1, 1, 0, 0, 0. V2 is equal to 1, 0, 1, 0, 0. And V3 is equal to 1, 0, 0, 1, 1. Okay, so we have three vectors. They are in R5, or we could say they are in C5. They're in C5. And actually, to make it actually, complex, I'm going to say this is 1 plus I here. Okay. All right. So, and then maybe 1 minus 2I like that, at least for this example. Okay, so these are three vectors. What's the linear span? Okay, so the linear span is going to be the set of all linear combinations of them. So C1 times 1, 1, 0, 0, 0 plus C2 times 1, 0, 1 minus 2I, 0, 0, and then plus C3 times 1, 0, 0, 1, 1 plus I, and this is going to be for C1, C2, C3 in complex numbers. Okay, now again, we could write it like this, or we could write this in kind of matrix form, which is the way that I like to write it. So 1, 1, 0, 0, 0. That's this first column goes to the first column of the matrix. Or sorry, the first vector is the first column. The second vector is going to be 1, 0, 1 minus 2I, 0, 0. And then over here, we're going to get 1, 0, 0, 1, 1 plus I. Okay, so let me just take a moment and rewrite this kind of head on so I can have it be straight 1, 0, 1 minus 2I, 0, 0, 1, 0, 0, 1, 1 plus 2I, and then times C1, C2, C3, such that this vector C1, C2, C3 is in three-dimensional complex space. Okay, so this is how we could write this. Now I will let you show for yourself that these vectors V1 through V3 are linearly independent, and they span some three-dimensional subspace of R3. Of C5. is spanned a three-dimensional subspace of C5. So what does that even mean when we say a three-dimensional subspace? Well, my claim is that these three vectors form a basis for their linear span. So they already, by definition, are a spanning set for their linear span. And I just mentioned that they are linearly independent. Okay, and again, that's something that you can convince yourself of. Okay, solve this equation. You know, if you set this equation times C is equal to 0, the only solution you're going to get is 0, 0, 0. So that's something that you can do to sort of remind yourself, you know, the connection between systems of equations and matrix vector multiplication, which is something that I'm going to talk about later on in this course, but it's something, again, that I'm expecting that you already are familiar with. So they are a linearly independent spanning set for their linear span. So according to the definition that I gave before, they are a basis for this vector space. They are a basis for their linear span. The number of vectors, maybe I can put the definitions over here, just scoot it over a little bit. The number of vectors in a basis for a vector space is the dimension of that vector space. Okay, so the number of vectors in a basis for a vector space is the dimension of that vector space. So there are three vectors and a basis for this vector space here. It's a subspace of C5, and so it forms a three-dimensional vector space. Okay, so now one of the things that we're wanting to do then is, let's say we have these three vectors, and we have some other vector. So let's say we have some other vector in C5. So let's say I've got the vector 3, 1, 1 minus 2i, 1, 1 plus I. Let's say I have this vector right here, and I want to ask the question, is this vector in the linear span of these three vectors? And if so, what are the corresponding C1, C2, C3? So in other words, what I want to do is I want to try to solve this equation. So I'm going to have this matrix V again. So 1, 1, 0, 0, 0, 1, 0, 1 minus 2i, 0, 0, 1, 0, 0, 1, 1 plus I times C1, C2, C3. I want to solve this equation. If there's not a solution, it means this vector is not in the linear span of these three vectors. If there is a solution, that tells me what the coefficients C1, C2, and C3 are. And since we already did, again, show this for yourself, these vectors are linearly independent, there's either going to be no solutions to this equation, or there's going to be one solution to this equation. Okay, there's either going to be no solutions to this equation, or there's going to be one solution to this equation. Okay, so in other words, what this tells us is this is the way, if we knew ahead of time. Now I know this vector is in the linear span of these three vectors because this should just be the sum of v1, v2, and v3, unless I made an arithmetic mistake somewhere, which I hope I didn't. So this would tell us, I know this vector is in the linear span, and by solving this equation, it would tell us what the coefficients are. Okay, now this is true, we can do this whenever we have a set of linearly independent vectors. Now here is something that we like to do. This is where we get into, this is why, now I'm going to tell you, now is the time where I'm going to tell you why we like orthonormal vectors so much. So these vectors are not orthonormal. If you do the dot product of any of these two vectors, you're not going to get 0, except maybe, none of these vectors are not orthogonal to each other. That's why I have picked them for the Graham-Schmidt thing, which is what we're going to see in a later video. Anyways, okay, so I'm going to state this pretty abstractly. Assume that the vectors v1 through vm are a basis. And again, typically we want to do it like this with brackets when we talk about a basis. So assume that those are, they form a basis for some subspace of C5. It could be C5 itself. So a vector space is a subspace of itself. So it could be C5 itself. Also assume they are orthonormal. Also assume they are ON. So ON means orthonormal. So they're orthonormal, meaning they are pairwise orthogonal, and the magnitude of each vector is equal to 1. So we know if V is in the linear span of these vectors, in other words, it's in the subspace. So let's say if V is in the subspace. Whoops. Then we know that V is equal to the sum k equals 1 to m ck vk. And one way to determine what the ck's are, one way that we can determine what the ck's are is by, solving this matrix vector equation. But notice what else we can do. Notice what happens if I do the inner product of V with one of these. Let's say V and Vj. What am I going to get? Okay, well, V is equal to that. So I can just write here, k equals 1 to m ck vk vj, okay? Because look, this right here, this sum is just another way to write V. Now I can use the fact that this inner product is linear in the first factor. And so this is now the sum k equals 1 to m. I'm going to do this in 2 steps. ck vk, or sorry, this sum right here, this is right. ck vk comma vj. And now this is a scalar, so I can just pull this out and we get this. Okay, but notice what happens here. Vk, Vj, the inner product of Vk and Vj. K is going from 1 to n. J here is fixed. Unless K is equal to J, these inner products are all going to be equal to 0 because these vectors are pairwise orthogonal. So then the only term that's non-zero, or the only term that might be non-zero, is going to be the term corresponding to K is equal to J. And so we're going to get Cj times Vj, Vj. Okay, so I'm going to come back to this because you might be thinking, oh, that's equal to 1, so it's just equal to Cj. Yes, that's correct. But even before that, notice what this tells us. It tells us that Cj is equal to V, comma, Vj divided by Vj, Vj. So Cj is equal to the inner product of V and Vj divided by the inner product of Vj and Vj. Okay, now, in our case, Vj is equal to, the inner product of Vj with itself is equal to 1 because our set of vectors, in addition to being orthogonal, are normalized, so they have unit length, and so this is 1. And so yes, you are correct that this is equal to Cj. And so in this case, we just say Cj is equal to V, the inner product of V and Vj. So orthogonal vector, an orthogonal set of vectors are nice because we have this formula right here, but orthonormal vectors are even nicer because we have this formula right here as well. Okay, so that is why we like to have orthonormal vectors. Okay, so I want to continue this discussion on orthonormality for just one more moment and sort of show you how this typically gets used in practice. Okay, so let I'm going to call it V1. Let V1, the reason I'm calling it V1 is because later on there's going to be a V2 and V3 and so on and so forth. So let V1 be a vector in Cn. So let V1 be a vector in Cn. The orthogonal complement of V1 is the set of all vectors that are orthogonal to V1. So the way that we put this, it really should be, is kind of abuse of language and notation here. We really should say the orthogonal complement of a set. So the orthogonal complement of the space spanned by V1, that is all multiples of this, which is, we have this linear span here, this is the perpendicular sign, and so this is the orthogonal complement, is the set of all V's in Cn such that the inner product of V and V1 is equal to 0. Okay, so all the vectors that are perpendicular or orthogonal to V1. Okay, here's a fact. All vectors in C5 can be written, and uniquely, there's one way to do it, as, so let's say V is equal to some multiple of V1, and then I'm going to say plus C2 plus C2 V2, where V2 is orthogonal to V1. Let me just write it like this, where V2 is in the orthogonal complement of V1. Okay, so what we're saying here, if we have a vector in C5, we can write any other vector in C5 as a multiple of that vector plus something that's orthogonal to it. Okay, if we think back to real space, well, what this means here, my marker is a vector, my paper here, my notepad here is the orthogonal complement. These are all of the vectors that are orthogonal to the purple marker. If I draw a vector, here, these are all going to be orthogonal. And now what this says is any vector in R3 can be written as this vector plus a vector in my page here. Okay, so any vector, if you think about I, j, and k, any vector in R3 can be written as a multiple of k plus something in the xy plane, plus a vector in the xy plane. Okay, well, why is this true? Well, we can just show that it's true. We can compute what the C1 and the C2 are. So C1. Okay, so C1 is going to be equal to the inner product of V with V1, the inner product of V with V1 divided by the inner product of V1 with itself. And then C2, and then what are we going to get? That's what C1 is, and then so C2 V2 is just going to be whatever it needs to be to make this happen, to make this sum happen. So we know what V1 is. We know what this is. Really, the way that we should write this is something like this. Like that. Anyways, and this is what C1 is, and then what is V2? V2 is just going to be equal to V minus C1, where C1 is defined like that. Okay, and then their sum, trivially, is going to equal to V. The main thing that we need to show now is that this vector V2 is orthogonal to V1. Okay, and indeed, we can do that. Okay, we can do that. So if we do the inner product of V1 and V2 defined that way, so V minus C1, which is defined as V times V1 divided by V1, V1 times V1. Well, what are we going to get here? Well, we're going to use the linearity of the inner product here. So over here, we're going to get V1, the inner product of V1 with V. Now we have to be careful because it's skew linear here. So let me just do this in two steps. So it's going to be this minus V1, and then we're going to have V comma V1 over V1 comma V1 times V1. Now I want to pull this scalar out, but when I pull it out, I have to put a complex conjugate. So now we're going to get V1 comma V. Okay, so now what's going to happen over here? Well, when I pull this scalar out, I'm going to have, like I said, I'm going to have to put a complex conjugate over it. So it's going to be V1, a complex conjugate here. When I divide by V1, this is a real number. Remember, that's one of the properties of an inner product. So this is a real number, so I don't have to, the complex conjugate doesn't go there. And then it's going to be times V1 comma V1. Okay, now notice what's going to happen. V1, those cancel. And now here, we're going to have V1 comma V. And now we're just left with the orthogonal, or with the complex conjugate of V1. But remember, what the complex conjugate does to the order, it just swaps it. And so this is equal to V1 comma V. And now it's the same, we're subtracting the same thing off, so it's equal to 0. Okay, so this shows that V1 and V2, again, where V2 is defined this way, are going to be orthogonal to each other. And then, of course, C1 times V1, I mean, this is going to be in the linear span of V1. Okay, so this shows, in this case here, that given a vector, how we can decompose it into something in V1 and something in its orthogonal complement. Okay, but we can generalize this. And this is where the concept of orthonormality is going to really kind of shine, I guess. Okay, so so we've got V1 through Vm. Let this be an orthonormal basis. I'm going to abbreviate that as ONB. An orthonormal basis for a subspace of Cn. So V1 through Vm be an orthonormal basis for a subspace of Vn. Oh, and by the way, I just want to point out, I should have mentioned this before. You've already seen this if you've taken linear algebra. So what we've computed here, we are looking at the projection onto the vector V1, the projection onto the vector V1 of the vector V. So this is like this right here, this projection sub V1 is like an operator, okay? It takes in a vector and spits something out. This is equal to V, comma V1 over V1, comma V1, and then times V1. Okay, so this is the projection of a vector onto V1. So again, or onto the space spanned by V1. Okay, and geometrically, as you remember from your linear algebra class, this is going to be the vector in the linear span of V1 that is closest to V. Okay, so here's how we generalize this. Let this be an orthonormal subspace for C. Then all vectors in C5, in Cn can be written as a vector in this space plus a vector in its orthogonal complement. So let's say the subspace, we're going to call this the subspace V. So a vector in its orthogonal complement, which is V perp. And this is going to be the set of all the vectors in Cn such that the inner product, let me kneel down here, such that V, comma, actually let me back up, all of the W's in Cn such that V comma W is equal to 0 for all V in V. Okay, so in other words, when we looked at the orthogonal complement of a vector, it was a set of all vectors that were orthogonal to that vector. The orthogonal complement of a subset, or of a subspace, or more generally a subset, is all of the vectors that are orthogonal to all of the vectors in that set. Okay, so again, if we go back to the R3 example, the orthogonal complement of my marker is the notepad, but the orthogonal complement of the notepad is my marker here. Okay, so the orthogonal complement of a subspace is the set of all vectors that are orthogonal to all vectors in that subspace. Okay, so how can we do this? Well, the projection onto the subspace V of a vector V is defined as the sum k equals 1 to m V Vk Vk like this. So the inner product of V and Vk with Vk. Okay, and then so if we look at the vector, I'll call it W, if W is equal to V minus the projection onto the subspace V of little v, this is in the orthogonal complement. Okay, and I want you to prove that. The W is in the orthogonal complement of V. So this is something that I want you to convince yourself of. I want you to prove it. Just do the inner product of W with any vector in this basis V1 through Vm. So that inner product is going to be 0. If you know that a vector is orthogonal to every vector in a basis, then it's also orthogonal to every vector in that subspace. So there's sort of two things that you have to do. Step one, and you can do it in whichever order you want to. Step one, show that W defined this way is orthogonal to the vectors v1 through vm. And step two, show that if a vector is orthogonal to all of the vectors in a basis, or just a spanning set, but in particular a basis for a vector space, then it's orthogonal to every vector in that subspace. Okay, so there's another thing that the last thing that I want to say about the projection here. This is something that will turn out to be very important. It's something, again, that you should have seen in your linear algebra class. I know we teach it here at Texas A&M, but also I review a lot of syllabi from other universities and colleges, and this is not something that's always talked about in those colleges. So I'm just going to remind you, or tell you for the first time, that if we want to approximate if V is a subspace of Cn and V is a vector in Cn, then the projection onto the subspace V, which I defined over here, of the vector V is the best approximation of V by vectors in V. Okay, so let's say we have a vector little v in Cn, and for whatever reason we want to approximate this by vectors in some subspace. Then the projection of little v onto that subspace is going to give us the best approximation. Okay, so when I say best approximation, I have to say in what sense. There's different ways we can measure approximation. So I mean in the following sense, I mean it minimizes. If we look at the, that is, it minimizes the norm, the 2 norm of let's see, how do I want to write this? V hat minus V. This is the 2 norm where for V hat in the subspace V. So in other words, V is our fixed vector. If we look at all of the V hats, all of the vectors in our subspace V, if we look at all of the V hats in our subspace V, the one that minimizes this is going to be when V hat is equal to the projection of little v onto the subspace V. Okay, so this is why we care about that. So now why would it be in a situation where we want to solve something like this? This is going to be, in terms of systems of equations, it's going to be in a setting where we want to solve like a matrix vector equation, mx equals b. But the vector b is not in the linear span of m. Okay, so there's no solution, but what we want to do is find the x that will get us closest to that. Okay, so if we have an equation like mx equals b, if this has no solutions, one thing that we can do is solve this equation. Mx is equal to the projection of b onto the space spanned by the columns of m. Okay, and then this vector is the closest vector in the subspace of the columns of m to b, and then we can solve this equation. Okay, so if you didn't follow that last part for now, that's fine. I'll say more about that later. That's going to be it for this video. I think I'm just going to do a couple more videos for this week. The next one that I'm going to do is going to be over the Gram-Schmidt orthogonalization process. But again, really nothing that I've said so far should be new. If you've had a linear algebra class, all of this should be things that you've seen before, and it should be refresher and review and that sort of thing.